Good day and Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to present a paper entitled How Many Chevrons Apart for Safe Lane Changing. So this paper is prepared by Nurul Ashkin Osman, myself, Ahmad Lutfi Amri Ramli, and Mat Yus Halifi Misro. We are from University Science Malaysia. First and foremost, when we are referring to chevron, we could be referring to two particular parts, which you can look from the slides. On the left one, you can see the chevron road sign, and the other one, there is a chevron that's been drawn on the road. In this particular paper, we are not referring to the left one, but instead we are looking at this particular chevron. Chevron is a sign mark on a road that is supposed to advise road user to put distance while following a car in the front. So it is designed to achieve required speed reduction or maintain a safe distance to avoid collision. As far as I'm concerned, and as you probably notice, we don't have chevron on the road in Malaysia, but there's one in Denmark. Here is a picture of chevron on the road in Japan, Yodogawa River Bridge. This is in early 1990s. This is in Wisconsin, USA in 1999, and this particular picture is in Denmark. So one of the common road signs for the road with chevron is that it will say keep apart two chevrons. It implies that if you are following a car, you should be able to see two chevrons to maintain a safe distance. So why is it important? This particular chevron is being drawn in between 35 to 40 meters, and a modern car may take less than 40 meters to stop. For example, when a driver is driving at 130 km per hour, the driver must see two chevron marking, that is 36 to 40 meters. Therefore, if the car needs to brake immediately, then it will be able to stop before it hit the car in the front. So that's the concept of having yourself separated two chevrons from the following car. In contrast, let's say in Malaysia, when we go under training for the license, then we've been instructed to count 1 Mississippi, 2 Mississippi, or 1,000, 2,000, and so on, so that we are able to separate ourselves with the car that we follow. So the question here, how many chevrons apart for a safe lane changing? Through our literature survey, we found out that most literature are talking about a safe stop distance when it comes to chevron. But what happens if you want to change lane to the right? So how many chevrons apart so that we can overtake safely? As you can imagine here, if you are driving at a certain speed, then there should be an appropriate amount of distance before you change lane. For instance, if I'm driving about 90 km per hour here, maybe if I go to the right, if there's no car on the right, that should be okay. But let's say if I'm driving about 90 km per hour and then I'm this close before I change lane, then it's not going to be safe for me if I keep my speed at 90 km per hour. It's different if I'm slowing down, then it's going to be safer. Now, so the question now is, with this particular speed, what is the distance that is safe for me to change lane? As you can see here, so it's much more difficult when it comes to deciding the distance like this. In this paper, we calculate the distance, but there's no telling from a driver how far it is. Therefore, to make it more applicable, we ask in terms of chevron. So how many chevron apart for safe lane changing, so that when a car arrives like this and it want to change lane to the right, then it will be able to change lane safely. This is how it looks like for a road with chevron. In the country that implements chevron on the road, they will do it in the highway. So both roads travel in the same direction. So we are going to look at what is DS, the distance between the following car and the leading car. Currently, my research area is computer-aided geometrical design, where we deal with curves and surfaces. So we are looking into various types of curves that can be implemented in terms of road safety. These are papers that are talking about different kind of curves that have been used in the context of road safety. So in this paper, cubic Hermat spline CT which has two different components in x and y direction, CXT, will be used to model lane changing maneuver by extracting speed information. So these are the formula that we are going to be using. So let's say we have point 1, point 2, point 3, and point 4. Then cubic spline will interpolate through the particular points. But it's different with cubic Hermite spline because we only define first and last point. Then imagine this is a road. So what we would like to do is that we also have the direction at the given points. So the first point, we have the direction here, and also the last point, we have the direction here. So by having this information, we can use cubic Hermite spline and generate the curve that pass through these points. So imagine that this is a car. We would assume that this is the path for a lane changing to get here. Furthermore, the two tangent points can be represented as a velocity vector because the velocity of the vehicle is defined as the rate of change of the path traveled by the vehicle whose position is ct with respect to parameter t. We show a visual representation of lane changing trajectories with different velocity. So for instance, the blue one, 70 km per hour, this is in meters. If someone's driving 70 km per hour, then you can change lane a bit smoothly. But let's say if you drive very fast, 150 km per hour, then it will go a bit further here and you will have to make a sharp turn if the distance here is very small. So all of this can be constructed by cubic Hermite spline. Technically, you can also do it with different curve as well, as long as it fits the requirement that we would like to have. So how do we do this? I'm going to talk about design speed. So the road is designed according to a safe speed limit. A basic principle of horizontal curve design is derived from the application of kinematics equation, which then leads to a design speed formula. For design speed, we can also find it in the JKR manual. So what does it imply here? So if we have this particular winding road and you want to find the speed limit, which is correlated to design speed, so we can compute by using this particular equation, Vd square, which is design speed, E is super elevation rate, and F is side friction coefficient. But the one that we should pay attention is DC, which is degree of curvature. Degree of curvature implies that if this is curvy, then the curvature will be big. Therefore, when this value is big, then design speed will be smaller. So imagine if you're driving on a straight road, then degree of curvature will be small. Therefore, design speed will be higher. So the important part of design speed is that in the road construction, we can decide the speed limit and then we can design the road. So for instance, if you want to create a highway where everywhere can be driven 110 km per hour, so we have to make sure that it reaches a certain degree of curvature. All of this is already being written in the JKR manual. On the other hand, for the existing road, like this one, we can find out and calculate the speed limit. So to calculate speed limit, we just basically find the value of E, F, and DC, and we will have the speed limit. So what do we do is that, imagine that this is the existing road. We can simply find the CT in terms of mathematical equation. For instance, this particular yellow curve. Then, by having CT, we can find curvature K, and from curvature K, we can find radius R. From radius R, we can find degree of curvature, and from degree of curvature, we can find velocity or design speed. Therefore, by constructing a curve here, we will be able to find design speed at each point that this curve passes through. But what's the deal with our chevron? Because chevron is usually on a highway where it is a straight road. Therefore, in this particular research, we do assume that lane changing behavior mimic the way a vehicle is moving on a curvy road. As you can see, when we change lane, it will create a pattern similar to driving in a curvy road. even though the road itself is straight. By this assumption, we are able to compute design speed for any curve that we generate. For instance, let's take a look at this curve where V0 and V1, the first and end speed, is given as 70. So when we generate this curve, we will be able to get the design speed for all points on the curve. Once we plot it, this is design speed for the blue curve. What it signifies is that when it's passing through the curvy part here, you have to slow down. When the path is a bit straight, then the design speed will go higher, which implies when it goes to infinity, it just implies that we are passing through a straight line. Therefore, looking at this blue line, when someone's driving with 50 km per hour, he or she is driving under design speed, which implies that the driving doesn't exceed speed limit in that particular trajectory. But let's say if someone drives at 100 km per hour here, it implies that he or she is driving dangerously until only somewhere over here. So driving over speed limit, as you guys know, may result to derailment or accident or skidding. So using this concept, we are looking at test number 1, which is BS. Here, the distance is 75 meters. As we assume that distance between two chevrons is 36 meters, so 75 meters is a bit over 3 chevrons apart, which is 36 times 2 equals to 72, so we take 75. We plot the trajectory for different driving speed, which is 90, 100 and 100 km per hour. But as you can see, we cannot distinguish much because it seems like it coincides with each other. However, design speed for the trajectory that we calculated and plotted. So as you can see, this is 90 km per hour, this is 100, and this is 110 km per hour. When we use 90 km per hour, this orange line, then at all points in this trajectory, design speed will be over 90 km per hour. What it means is that if someone is taking over with 90 km per hour while maintaining its speed 90 km per hour along this trajectory, then it will always be below design speed. So this is okay, this is safe. Next, if someone's driving at 100 km per hour, keep the same acceleration throughout the trajectory. The same thing goes that it's still under design speed. So this is still a safe lane changing. But what happens if we let it to be 110 km per hour for a distance 75 meters? At some point, design speed is lower than the driven speed. So if he or she drives at 110 km per hour, at some points over here and here, it is prone to skidding or derailment. Therefore, if you are 75 meters away, 3 chevrons apart, you should not be driving more than 100 km per hour. The same thing goes for ds equal to 36 meters. In this case, this is 2 chevrons apart. Similarly, for v equals to 40 km per hour and v equals to 50 km per hour for 2 chevrons apart, then these two lines will still be under design speed, which means that if someone's driving at 40 and 50 km per hour, it will still be a safe lane changing. But if someone starts driving at 60 km per hour, then you can see that design speed is lower than the velocity that he or she is driving, so it's not safe anymore. So it comes with simple conclusion: how many chevrons apart for safe lane changing? If you are driving at 2 chevrons apart and you want to do lane changing, shouldn't go more than 50 km per hour. Not precisely, because we do at a jump of 10 km per hour, which can be an improvement in the future. Or if you're driving at 3 chevrons apart, you should be driving more than 100 km per hour if you want to change lane. So that's basically it. That's our presentation for how many chevrons apart for safe lane changing. Thank you very much.